Hey everybody, and welcome. In today's video, which we are recording on this very cold Saturday, will be about the lungs, and we're going to use the partial derivative to calculate blood flow through the lungs. And so I have here a 3D rendering of a high-resolution CT scan of the thorax region of the body. And so we can see that the arteries and veins, and then here's the heart. Here's another image, a clearer image of what is going on. You have the lungs here, the blood vessels leading to each of the lungs. You have the heart and the aorta. And so on average, the estimated blood volume in the lungs is about 450 milliliters, or 9% of total blood volume in the circulatory system. This can fluctuate between half and twice that, or 225 milliliters and 900 milliliters respectively. And I wanted to find an image that kind of illustrates how much 200 milliliters is, and that's what this perfume bottle is trying to demonstrate in comparison to the hand. Because you're not in person, you can't really see how big 200 milliliters is unless you have it something to compare next to. And so the human hand, most people know how big hands generally are. The volume inside this perfume bottle would be about 200 milliliters. And so that's that. And then also lungs rely on nerves from the peripheral nervous system to stimulate smooth muscles in the lining of the bronchus and the bronchioles. So here's the main bronchus, or left main bronchus right here, this white gray thing, and then mostly in this region because this is the anterior lobar bronchus. And then you do the same thing on the right side. We have the right main bronchus. Zoom in here. Right main bronchus right here. And so that's a little bit of anatomy of the lungs. And so let's do some partial derivatives involving blood flow through the lungs. And so researchers have developed a generic formula or equation or model of blood pumped through the lungs based on the quantity of oxygen, either that has just gone through the lungs, the quantity of oxygen that is used by the body in 1 minute, and the quantity of oxygen that is about to enter the lungs. And that equation is C, blood flow, is equal to B, so the quantity used by the body, divided by A, so the quantity that has just gone through the lungs, minus the quantity that is about to enter the lungs. And so here we have an equation. But we are curious how the amount of blood pumped through the lungs changes when we change one of these variables and keep the other constant. So let us assume that A has increased by 1 unit, 1 milliliter. And so we can find the partial derivative of C with respect to the partial derivative of A equal to the partial derivative with respect to A of B minus A minus V. And so we can rewrite this so that's a little bit clearer. Really what this can be rewritten as is this portion can be B times and A minus V to the negative 1 power. And so from here, we can find the derivative of this expression by maintaining A and V are constants. So they're not a variable, they're just, imagine like a numbered 5 or a 10 or 1,000, just a number. Whereas A is our variable, anything can be A, because that's what we're looking at. We want to know how the output C changes with a change in A if we keep everything else the same. And so we use our derivative properties, and it looks like we have a inner function and outer function. So the derivative of this will look something like b times u to the -1. Use our power rule, -1b. So this is equal to -b times u to the -2nd power. And then we need to find the derivative of u. And multiply this by the derivative of u. That is the chain rule, because we have an inner and outer function. And so we get, sorry about the dog, I don't know if you guys can hear him. This is equal to -b times a minus v to the -2 power times the derivative of u, which is the derivative of a minus v. V is a constant, so that just goes away. And a just leaves us with 1. So that is times 1. And so this is equal to -b over a minus v squared. Because it's a negative exponent, we can just bring it down as a denominator. And this is our partial derivative with respect to a. So if we insert some values, let's say that b is equal to, let's say b is 200 milliliters. Let's say a is changing from 160 to 161 milliliters. And let's say v is equal to 125 milliliters. And so we have already derived our partial derivative expression. And so if we just plug these guys in, we get -200 over 160 minus 125 squared, and this equals -200 over 35 squared, which equals, let me calculate that for us. That equals roughly -0.16 milliliters. So the total C will decrease slightly by 0.16 milliliters if we increase the amount of oxygen that had just gone through the lungs. If we increase that, we'll decrease the total amount of blood volume pumping through the lungs by approximately 0.16 milliliters.